Hi, so in this video, I'm going to talk about the relationship between acceleration, speed, and a distance. Let me just share the note. Okay, I'm going to continue this. Okay, so the definition of acceleration is the change in velocity per time period. So that's the acceleration is the change in velocity per time. The velocity contains both the information about direction of motion and speed. But to talk about magnitude of acceleration, in the previous, in a part 3 video, I discussed about the direction of acceleration by looking at the change in velocity. Here, I'm going to just talk about the magnitude of acceleration. So magnitude, which is not the direction, right? The magnitude of acceleration. Let me just write it first. The definition of acceleration that's equals to change in velocity per time. So if we want to find out, it's okay. If we want to find out, this is only for the case if we want to find out the velocity of the object that's going through acceleration. This line is completely. If we want to find out the velocity that's going through acceleration, then if the acceleration is constant, so this is only true for constant acceleration. This is only true in constant acceleration. Then you can find the velocity of the object is equals to acceleration, the constant acceleration, times time. What's the unit of acceleration? The unit of acceleration is meter per second square. And what's the unit of a time? That's second. And what's the unit of the velocity? That's meter per second. So you can see the meter per second square and times the second makes it meter per second. So this makes sense. So this is only when you have a constant acceleration. If the acceleration is changing with time, if you might be going faster, slowing down faster or something, then you actually have to take an integral, what we say integral. But if you have a constant acceleration, the acceleration is constant, means it's just going faster, 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 faster with the same rate in change in speed or slowing down in the same rate in a speed. So if you have a constant acceleration, then the velocity is acceleration times time. What is the example? We have learned about the one of the famous example of constant acceleration. What kind of a motion is going through a constant acceleration? Free fall. Free fall, when the object is in a free fall, its acceleration is 0. Is it no change in motion? No, it goes down faster and faster. It has a constant acceleration. So for free fall, right? We said that acceleration object is falling and it has an acceleration that's at the constant g, which is gravitational acceleration. What's the value? 10 meter per second squared. Any objects has the same acceleration, 10 meter per second squared. So the speed of the object in free fall is equals to, what do you think? G times T. V equals G, which is 10 meter per second squared, times T. So as the object falls, it increasing in speed 10 meter per second each second. So if I let go the pen, initially this pen is at, the speed is 0. Then I let go the pen, each second it increasing in speed 10 meter per second. It goes faster, 10 meter per second, 10 meter per second each second, faster and faster as it keeps falling. So let's see, if I have, I'm holding an apple, let's say, right? There's the apple here. I'm holding an apple. And then if I let go, what is the speed of the apple? After 0.5 seconds later, we say the speed of the apple is the acceleration, constant acceleration, in this case, g times time. So the speed of an apple at t equals 5 seconds later, that's g is 10 meter per second squared times 0.5 seconds. So the speed of the apple is equals to 5, what's the unit? Meter per second. So the 0.5 seconds later, it let go, it has the speed of 5 meters per second. How about if it let go, what's the speed? T equals 2 seconds. Then the speed increases 10 meters per second each second. 10 meter per second squared times 2 seconds, right? What's the speed? 20 meters per second. So that's the relationship of the speed and a constant acceleration. When you have a constant acceleration, speed picks up each second with that constant acceleration. And when the object is in a free fall, the acceleration is always 10 meters per second square for any object. It could be apple, it could be bowling ball, it could be elephant, it could be you. Anything that's in free fall has the acceleration 10 meters per second square. The definition of free fall is only gravitational force, no air force, air drag force, no friction forces. So you can find the speed of the free falling object. How about the distance? How much it drops? So for constant acceleration, so again, this is only for the case of the constant acceleration. For constant, if it's not constant acceleration, we have to use an integral. But if it's constant, for constant acceleration, and such as free fall, when acceleration is g, and that's 10 meters per second square, right? Then the distance, only for the constant acceleration, the distance that traveled that's equals to 1/2 times that constant acceleration times t, time square. So I'm going to say distance d is equals to 1/2 times acceleration times t squared. Again, what's the unit for the acceleration? Unit of acceleration is meter per second square. And then you times that with what's the unit for the time? Second. So, but we have a second square, right? Now we have a second square. Take a look here. Second square. So we have a second square. So meter per second square times with the second square is equals to meter, which is the unit for the distance. So this makes sense. Why do we have the 1/2? That comes from integral. So you gotta go through the very precise definition using calculus. Then you're gonna see why there is the 1/2 a acceleration times t squared. So in the case for the free fall, again, oh my gosh, for free fall, acceleration is g, which is 10 meters per second square for any object. So the object that's in free fall will drop for 1/2 times g times t squared. 1/2 times 10 meters per second square times t squared. This is again true for any object. It doesn't matter its mass. Any object in free fall will fall with this amount of distance with the same constant acceleration. So again, we said that apple, there is this apple here, right? And this apple is let go, it's dropped. So it fell, and then it fell after, what was it, 0.5 seconds? When t equals 0.5 seconds. When the t equals 0, what's the apple's velocity, speed? That's equals to 0 meters per second. Y equals 0. And then when the apple is 0.5 seconds, the speed was 10 meter per second squared times 0.5, so it's 5 meter per second we did. How much did it travel? That's equals to 1/2 times g t squared. So y is equals to 1/2 times 10 meter per second squared times 0.5, second squared. So I'm going to write it. Here. Y is equals to 1/2 times 10 meter per second squared times 0.5 second squared. So y is equals to 0.25 times 5. So it becomes 1.25 meter. What happens at imagine this though. So I'm going to show, this is called motion diagram. Each dot represents the location at that time. So imagine if we have an object, like for example, the ball is rolling horizontal surface. That means what kind of a motion is in? It's in constant motion. So constant motion, we draw this motion diagram. Of the object. So these dots has a equal spacing. So it's almost like you're taking a picture of a same time interval. So you're taking a picture at the same time interval and you superimpose it on top of each other on the same picture. Then you see that an interval between these dots is equally separated. So that's when they're in a constant motion. And once they're in incline, how does this motion of the ball look like? This one is going to be, next one is going to be maybe here. But you think the spacing is going to be the same if there's no air resistance or friction force? The spacing will, in fact, should keep increases because now it's accelerated. It has acceleration, so speed increases, right? And then in fact, if you make it even more tilting, then this spacing will be more exaggerated. So same thing with the free fall. When the object is completely vertical, right? Then they're gonna be going faster. Something like that. So the distance of a falling distance will not going to be in a constant increments. It's going to be bigger and bigger by t squared. So the apple at 1 second later is maybe at here, but then at 2 seconds later, it's going to be even, went down even more. 3 seconds later, it's going to go fall even farther. It should be even more. This is very extreme. So maybe I could have drawn like this and then this, something like that. So it goes by free fall. This is the case for the free fall. The distance, falling distance, is linear to t squared, not t. Okay, so this is going to be the end of this video, and I guess I'll see you in a discussion.